So this is part of chapter 2. So I'm going to go over nonpolar, polar, amphipathic molecules. Amphi means ambivalent, right? Like amphibians who live both on land and water. So these molecules are both polar and nonpolar. And I'll also talk about water in this segment. So we went over covalent bonds, and where we said covalent bonds may be polar or nonpolar. Nonpolar are the ones which equally share their electrons, like carbon, hydrogen. You have methane, or even like if you have something where you have double bonds between the carbon atoms and it has hydrogen attached on the sides. Those bonds are also pretty strong and they are still nonpolar. Okay, so you have equal sharing of electrons between the atoms, or oxygen molecule, or nitrogen, right? And triple bond N. All those are nonpolar. And we also saw in water where we have oxygen and hydrogen within a water molecule. That's a polar covalent bond, where at any given point of time, oxygen is trying to snatch the electrons to itself because oxygen is the most electronegative, right? It has more pull because of its 8 protons over the 2 protons that the hydrogen has. So nonpolar molecules may have covalent bonds. For example, you have carbon dioxide, okay, so they will cancel each other out. So let's look into some amphipathic molecules. So these are molecules which have both polar and nonpolar ends. And the best example for this are phospholipids. Phospho, which is the phosphate group that has negative charge to it, and then lipids, which are fats. So we're going to be talking about phospholipids in a little more detail when I go over the macromolecules. So phospholipids are the best example for amphipathic molecules. So this picture shows how you have the glycerol attached to 3 fatty acid chains, and I'll talk about it in detail when I go into biomolecules. And then you have a polar molecule, like one of these fatty acid chains is replaced by a phosphate group. Okay, so here you have the phosphate group. So this is negatively charged because of the oxygen that it has. So that is going to repel the non-polar fatty acid tails that the glycerol has. So this 3C carbon compound is called glycerol, and it has 2 fatty acid chains which are in completely opposite orientation to the phosphate because these are negatively charged and these repel anything that is hydrophilic. So this is an example of an amphipathic molecule. So when I'm going to talk about water, we will talk about water being a universal solvent. I don't like to use the word universal because there are some things which do not dissolve in water, like nonpolar molecules. So these are called as hydrophobic, meaning water fearing. For example, if you add a drop of oil in water, it's not going to mix. It's hydrophobic. But how do we carry fat in water, like inside our body, like in the blood, right? Blood is mainly made up of water. That we have some things like, so we have cohesive water molecules that force out the nonpolar molecules. What this means is the hydrophobic lipids can travel in the blood only if they are attached to protein molecules. So it's kind of an amphipathic molecule, but not really because the lipids are completely enclosed within a protein molecule. And fats and cholesterol, right? Fats like the digested fats, those are covered by proteins and they form what we call as chylomicrons. And then cholesterol, those are attached to proteins called as lipoproteins, right? And then, like for example, we have HDL or LDL, so low density lipoprotein or high density lipoprotein, depending on how many proteins they have. So the fats and cholesterol, they don't have to really travel in the blood. They're covered by proteins, which allow them to be carried in the blood. So amphipathic molecules, they partially, really, they don't dissolve in water, but they can orient themselves. The polar side of the molecule orients itself towards the water. So polar portion dissolves in water and non-polar portion is repelled by water. Phospholipid is amphipathic. So the polar heads, they are in contact with water. So phospholipids make the the plasma membrane, and plasma membrane or any membrane for the organelles, they are made up of lipid bilayer. And when we're talking about the bilayer, the polar heads are facing the water. There's water everywhere in our body, inside the cell and outside the cell. So polar heads, they are in contact with water, and the non-polar tails, they face each other. So this results in a bilayer of phospholipid, and this is called, for example, in the membranes of the cell. Other amphipathic molecules form a micelle. I wish I could draw this. So micelle is something where it forms like a rounded structure where the polar heads are facing the water and the tails are inside. Let me see if I can find some structure. Okay, so this is a micelle. So here you have the phospholipid head, right? This is a phospholipid. You have the phosphate head, and these are the two tails, fatty acid tails. So these can orient themselves towards oil, right? So if you have water outside, so the phosphate heads are going to orient themselves towards the water. And if you have water inside, of course, they're going to completely reverse and face the water, meaning the polar heads are going to face the water and the non-polar tails are going to face the oil. This kind of structure where it forms like a bubble, right, in water is called as a micelle. Now, this is a phospholipid bilayer for plasma membrane. So plasma membrane is made up of two layers, okay, of the phospholipids. So this is outside the cell, right? So there's water here. This is inside the cell. There's water here. So the phosphate heads are going to orient themselves, okay, to be facing the water, and the non-polar tails, they face each other. Okay, so this is how it looks around the cell. So that is your amphipathic molecules.